This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology
With experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University.
When we think about chemistry, most of us picture something we can see, maybe bubbles rising in a beaker or colors suddenly changing. But some of the most important moments in chemistry actually happen long before any visible reaction begins.
At the nanoscale, there's a hidden window of time right after light hits a molecule. And in that instance, electrons begin moving and energy starts flowing at almost unimaginable speeds.
Those motions happen so fast, they were once completely invisible to science. But Northwestern University chemist James Gaynor is building tools capable of capturing those events in real time using optical components he jokingly calls more expensive Legos.
His research focuses on the very first flash after light interacts with matter, across timescales measured in attoseconds and femtoseconds. By studying those tiny motions, scientists hope to better understand and maybe someday even guide chemistry from the very beginning.
And that could have major implications for technologies that we use every day, from solar energy to electronics and other light-driven materials. Here to discuss this new frontier is James. Welcome to Nanoscape.
Thank you all.
First off, we want to extend a congratulations. Faculty Early Career Development Award from the NSF. That's a pretty big deal, so congratulations.
Thank you. Yeah, I appreciate it. This is one of the ones I'm really particularly proud of. I mean, the National Science Foundation is, of course, a huge funder of research, especially for basic energy or fundamental research. And the Career Award's a really awesome one to be given because it's their vote of confidence, basically, in a trajectory that you're taking as a young faculty member.
How do you describe your research to people outside of science and academia?
Yeah, this is one of the ways that I like to think about it, at least. If you were to imagine yourself in the frame of an atom, let's say you were able to just sit on an atom, the methods that we're developing are allowing us to see what happens when electrons are like orbiting around you. And if you were to think about how long it would take one electron to just go one time around you, that would be what we would call 150 attoseconds. So it's a really short unit of time. If I was sitting on a molecule where now I'm on one atom, but there's another atom around me, if I thought about what time it took one electron to move around me by comparison to how much that other atom is moving relative to me, that electron is going to move about 1,000 times faster than it takes this other atom to move. Now, one of the cool things about our research is that we're developing methods that use techniques that are actually the fastest single events that humankind has ever actually produced. You need that level of time resolution in order to actually measure in reality the sorts of things that I just described. Really, what we're trying to figure out in a variety of molecules and materials is what is the relationship between those electrons that would be moving around me and the other atoms that are moving next to me. How do those things interact with one another in a way to transfer energy in directed ways, to give rise to new properties of materials that we might like, to interact with light in different ways? That's one of the most fundamental bases we have to understand how all of the things that we might be trying to engineer eventually and maybe put in devices or do other things with, what they're all based on. So we're trying to get at really the heart of how all of those things can happen.
This is fundamental research in some ways. And again, you're trying to get to that point where how can we engineer and build things around this? Take me back to your youth. Were you always interested in how things work, building things, engineering new things?
I got what I would say really catching the chemistry bug when I got a research experience as an undergraduate at a national laboratory. The real thing that got me hooked on it was I was working at a facility people would call an international equipment user facility. So the Department of Energy basically put uber amounts of money into developing the world's best measurement capabilities for a whole range of different measurements. And so people from around the world will fly in to use those capabilities. It's a really cool way to see what the international scale is. The scope really, I would say, beyond international boundaries is for doing science. I saw that really early and I was like, this is so cool. Like the science is really cool, but the atmosphere and what you can do with it, people you can meet doing it is really cool. So that kind of got me hooked on what I would say is the beginning of the trajectory towards wanting to do research. But before that, I wanted to be an architect, actually. So my story to connecting those 2 points, basically, my dream in high school was let me be an architect, to where I ended up going down the research and chemistry route. It's a pretty roundabout story, to be honest. But I would say the connecting feature throughout, the theme that really sought that connection was I was always interested in how structures behaved. At the architectural level, what I was interested in doing was figuring out how I could build a really cool, structurally sound thing, usually in the form of a house or a building or something, but that also had a real aesthetic beauty to it. Something that was maybe, for example, Frank Lloyd Wright's Falling Water House. It looks like it should fall basically into this waterfall, right? But somehow it doesn't, and it's just a really cool building. Or a whole number of other examples where you're like, that thing is some blend of art and engineering that makes it an attractive thing to just look at and exist in, but it's also going to have all of these structural properties that actually allow it to be a sound building. So that was fundamentally something that just really interested me. But when I was in my general chemistry course and started learning about basically how chemical bonds can be formed and how geometry plays a huge role in forming the molecular structures that we know about and can measure, I saw the connection basically between what was happening at the molecular level in the same sort of vein that I was really interested in architecture. Basically, what is the structural parameters to create something that macroscopically is really, really cool, maybe has some properties, maybe it looks a certain way, maybe it does a certain thing, and that we could relate that all the way down to like a way smaller scale than I had ever thought of. I would say that was the thing that was really putting me down the path of chemistry, and in particular physical chemistry. So going back out to the national lab part, I was in a research laboratory that was next to a laboratory that had a bunch of lasers in it. And so that was the first time that I ever really saw what large-scale laser facilities look like. It was a huge room. There was a whole bunch of different optical tables, which are basically these maybe 2 feet thick, monolithic, like breadboards of 1 inch by 1 inch bolt holes. And everything, to include the starting laser on one side of the room, everything was custom built all the way down the room to perform these really high-end experiments. And so I just thought that was the coolest thing. And so, Erin, earlier you had mentioned the idea of Legos and how that was part of some of my interests. When I saw that, I was like, these are just like really expensive Legos. You're just building
laser Legos.
They're laser Legos, yeah.
Two awesome things.
I guess it helped that I, as a child, really enjoyed playing with Legos. That's a connection, I guess, in a lot of ways. I liked the creative aspects of, I got this bucket of all sorts of building blocks, and it's up to me to figure out what sort of cool thing I want to create out of them. But yeah, at the scientific level, now, as undergraduate James, I can get these really cool new types of building blocks to build an instrument that's going to allow me to study things that I couldn't otherwise see unless I built the instrument to do it. I don't know. When I look back on it, I think there's just all these different influences and passions that kind of melded in a unique way that sort of put me down this path.
We love hearing about the sort of art and science intersections so many of our scientists have at Northwestern.
It's like all of them. I feel like every single person we've spoken to has this pivot. We're like, do I do this art form or do I go into the hard science? So I'm curious, if you're at a dinner party, do you describe yourself, I'm a chemical architect or nano architect, kind of combine those two things so you can still feel like an architect?
Maybe I should. I don't. I think it's because now I'm probably a little bit too well attuned to being a measurement person rather than somebody who's actually like making new materials. In my lab, the building creative aspect of it is not as much on how do I, as for example, say like a synthetic chemist, how would the synthetic chemist go about actually building a new material? To me, what my amazing colleagues do for actually synthesizing new molecules and new materials, to me is still just the most amazing magic ever. I am just constantly excited by these new things that they are like, oh yeah, we made this thing and it has, we think, these new properties. The types of experiments that we're capable of performing in my lab are going to really open up a completely new understanding of what you just made. Because usually in our experiments, we're measuring things directly that you can't really measure any other way. And we design those experiments so that we can actually access that information because we think it's important for guiding developments in materials or new molecules or what have you. No, I don't say that, but maybe I should, as long as I'm not in the presence of some card-carrying synthetic chemist, because I think they would call me out for that. Yeah.
Some eyebrows would be raised, yes.
Yeah, but as long as I have a cool picture of my laser lab with all of the stuff that we built, then there's a little merit to that.
So your research, again, happens at the attosecond and femtosecond. How do you help people understand just how fast those moments really are?
I think comparisons are basically your friend here. How do the motions of materials or molecules that we are interested in, how do those different motions within those materials compare? And so really on the electronic timescales, for the most part, what I would say, as far as chemists really want to dive down into further reductionist perspectives of a material or a molecule, usually electrons and protons are kind of your fundamental particles to deal with. So if you think about an electron moving, that's going to be its natural time scale is going to be on the attosecond time scales. So that's usually tens or hundreds of attoseconds. So a fraction of a femtosecond. Now, if you think about how long it takes different atoms to move with respect to one another in something like what we would call a vibration, that's usually at the fastest, it's usually like 10 femtoseconds or something. So if you're thinking again in comparisons of when and how fast do electrons move versus how does the whole skeleton of a molecule, if you will, change its basically like spatial configuration. There's roughly a factor of 1,000 to 10,000 in terms of difference of timescales. The electrons moving really, really fast and the vibrations or the molecule moving 1,000 to 10,000 times slower. Like I had mentioned earlier, we really have to develop in some ways a shutter speed of a camera that is a well enough defined moment in time to be able to actually measure the time scale of something else. If you think about it with the camera analogy, I can only actually resolve things in time that are slower than what my shutter speed is. Otherwise, a lot of things are happening when my shutter is completely off or when it's completely on that I'm not going to actually be able to tell anything about. So the laser science development is really geared towards developing shorter and shorter pulses of light. Basically, the light is only on for, say, a couple femtoseconds or a couple hundred attoseconds. Those laser capabilities are actually currently present downstairs in the basement of tech, right, in my lab. So we can do that. The next thing is, once we've generated those like shortest moments in time that we can basically use as humans currently, how do we put them together to understand that physical picture of electrons are moving really fast and the motion of the molecular skeleton is moving really slow by comparison? How is it that the electrons notice what's happening to the structure of the molecule as it changes? So the attosecond to femtosecond timescale really, I would say, on the most fundamental ground, like that's where all the action is happening. It's pretty much the most initial conditions for any sort of consequent behavior down the line in time that would happen. So when we're thinking about, for example, how do we design a device or a material, or even just understand a molecule's behavior when light from the sun hits it? In principle, some of the things that we should have to be aware of are really just what is the most basic level of interaction between that light and the material. Can we understand it? And if we can understand it, could we then control it or even predict what the properties would be in other things that behave like it, right? Ultimately, we want to have some sort of structure, function, relationship in that vein for anything that we're going to try to engineer up, scale up for different types of eventual applications. So that includes nanomaterials, that includes just molecules. I think it's pretty all-encompassing of an approach.
Well, just to jump off of that a little bit, take us inside that very first instant when a photon does hit a molecule or material. What is happening? What do we know is happening first?
Oh, great question. So we chemists, I would say, in a lot of ways, resolve ourselves to models that tell us how electron densities, so areas in a molecule where the electrons like to hang out, what those look like. And we use that as a way of characterizing the states that molecules or materials would exist in. And when light becomes incident on a molecule or a material, we usually think about the electronic distribution, so where the electrons are hanging out in the molecule. We think about that changing. So it goes to another state where the electrons, rather than hanging out like on the tennis court in the pool, they like to go to the bar. Let's just say that some light is incident that transitions everybody from the pool to the after party. In that analogy, people are going to move slow, right? People are going to hang out and chat with one another. They're going to ask questions about, is it the right time to leave the pool because I'm really comfortable in the pool? They're also going to say, I'm like only midway through my tennis match with my buddy and I really want to win before we go to the bar because I want to have that bragging right. This is like an over personified way of saying the particles that we think about also will interact with one another. They will also be a product of their environment.
And I have seen people move that fast from the pool to a bar before.
It depends, right? Yeah, exactly. That's a good clarification there, Seth. Let's say that outside the bar, somebody's throwing another party, and from the time that the light hits the people in the pool and at the tennis courts that triggers them to want to move to the bar, this much slower motion of somebody bringing in like a bouncy house. Let's say it's a bouncy house in the middle of the pathway for everybody to get to the bar, right? So all of a sudden, everybody is held up because of this. If we think about what our comparison of timescales are just for a second, the motion of the nuclei in the molecule, right, are thousands of times slower relative to one another than the electrons. But let's go back to our pool party scenario, right? Now we've got this massive bouncy house that's just moving in front of where all the electrons are trying to go, or the electrons being the people. They're on their way to the bar. And that's going to pose challenges. So then the question is, if you're sort of like, I don't know, an observer, a fly on the wall or whatever, watching this whole thing happen, you're kind of wondering, all right, how long is it going to be before the electrons realize in their way over that like this bouncy house is in the way? And then what are they going to do about it? And the question is, whenever they do something about it, is the motion of that bouncy house going to be the thing that determines how everybody can or cannot get to the bar on a certain time scale? You're asking a question of, with things that can move really fast versus things that are naturally kind of slow, where is the interaction of those two things that ultimately give you like a behavior that you're interested in? Which in this case, I guess, would be how fast do people get to the bar? Hopefully that wasn't too esoteric.
I love a good visual.
So, all of this research that you're doing, how could this eventually connect to technologies that people are using in everyday life?
A current project we're working on is these very complex systems through collaborations with our materials research center here that have basically an organic molecule that's really good at conducting electrons. And then it's usually in the presence of ions, which are in an electrolyte. So the idea is if you have the ability for this organic molecule to move electrons along its molecular axis, the way that we optimize that performance is by stabilizing this pathway of the electrons with ions, so positive or countercharged particles. Maybe we take sodium chloride, like table salt, and dissolve it in water. And the positive sodium and the negative chloride, they dissociate in water and they stabilize around this molecule that helps electrons move. At a technological level, what we really want to know is how can we use, let's say, materials that conduct electrons to have faster responses of conducting electrons so that we can maybe, say, engineer computers to move a little bit faster. Or maybe we could basically separate charge so that we could actually create new electrical circuits for different types of applications.
So where would regular people actually run into this? What kind of devices are we talking about?
A lot of the applications are actually bioelectronic, where now we can use these materials. We can, say, either put them on the skin or even in the body to try and actually measure different types of properties. Let's say, I don't know, a blood cell count or like other types of, I would say, medical devices that give you more active and more accurate feedback on what levels biologically would matter for, say, treating, I don't know, a condition. These types of materials here were really based on the idea of just fundamentally, how do you create electronic motion in a more controlled way, in a more efficient way, using new building blocks? And then the idea is, if we could do that, could we take that concept and then put it into these different types of devices, say, where we could measure blood glucose or something like this?
Would you say the long-term dream here is to watch chemistry more clearly or to catch it early enough to change its course?
Oh, yeah, I would say both. I don't think that you could truly know how to change its course until you've done the former of what you said, to really see what's actually happening at the earliest moments. From my perspective, I think about that as, first, we've got to understand something before we can actually have a hope of manipulating or controlling it. Then you can actually think about controlling it if you have an accurate way of understanding it. And then if you have both of those things, you can put them together to predict what would happen under a completely different set of systems based off of guiding principles that came from understanding and controlling. In my view, the ultimate dream here is to actually see what's fundamentally the most basic way of doing chemistry, which is to play with the electron densities to see how they actually form bonds. But I would argue that what we should be able to do is understand really the initial conditions and then try to perturb them so that we could get different outcomes. I just don't think we're yet at the point where we really have the ability to have done that yet to answer that question. But I feel like there's no reason why that question can't be answered, and we should do it.
So this is the Nanoscape podcast. And as you're talking about all this, what the future could look like, do you think nanoscience is entering a new phase where time matters as much as structure?
Oh, yeah, absolutely. So there's a really cool parallel here with some of the work of Mark Ratner, who played a really huge role in getting the International Institute of Nanotechnology going. Both he and Chad Merkin were huge players in that. Mark Ratner's perspective of starting with the question of, if we just boiled down to the nano level and we asked, could we change the way that, say, metals behaved or electronic properties behaved by making them molecules that were conducting electrons, right? What would change if we did that? What would be be the consequences of miniaturizing a lot of sort of macroscopic properties that we know? So in some ways, that, Erin, as you said, that's a very structural question. We're just shrinking the length scales all the way down. You could start to understand how electrons would move at the molecular level on timescales that are much closer to the sorts of timescales we've been talking about on this podcast so far. So I think when you shrink structure, you still then influence the whole environment that all of the dynamics that ultimately give rise to the properties sort of have at their disposal. And so I would argue that you really do need to reconsider on timescales that are very directly pertinent to the dynamics you're after, but now on those short length scales. And when you boil that down, I think ultimately you're going to come to the conclusion of the electrons are really the things that we need to pay a little bit more closer attention to, which are going to take these really fast timescales.
As you said, you've called optical components more expensive Legos. What is the lab equivalent of realizing you have built the whole set wrong?
Oh, man. One way to answer that question is the lab equivalent to realizing you built the whole Lego set wrong is we are in the business as academics of training the next generation of scientists. And I would argue that if any child has gone through a Lego set and not built it wrong, then they haven't really learned what Legos are all about. Because that means that maybe they followed the instructions and got to like the place that they were told to go. But what they haven't realized is when they don't have an instruction manual in front of them, what are they going to do? In our business, we are really tasked with making sure that the students who are coming from our labs, I'll speak a little bit more from my perspective, so not to put this onto my colleagues' perspectives, although I'm sure many of them would agree. My perspective is that people who should be coming from your lab, number one, they should be very, very technically competent. They should know in and out everything about what they did, right? And that's almost always a given. They should also be really great people. I think we have a duty to train good citizens as well. And there's a whole wealth of opportunities for learning personal lessons during your research. For example, how to accept that you built the Lego set wrong. That's an important one, and it's difficult. One professor I had in graduate school basically just said to me at one point, this is early on, he said, look, there's nothing different between you and me. I've just failed a lot more than you have. So one way to answer, again, your question, Seth, is this is just the process of education, and it's a really important process that should not be taken lightly. I've told my students sometimes, if you're not breaking something, then you're not trying hard enough, all right? Now, there are certain things that are difficult to replace, so you shouldn't break those. It's really important that students have really dove in deep enough to have built the Lego set wrong, had to deconstruct it, realize why they should have put piece A in this position instead of where they did put it, and then rebuild it. And oftentimes that leads to new capabilities too, right? I think about it as from a perspective of trying to promote creativity. People need to have followed a train of thought or followed a curiosity to an endpoint and then realized, oh, okay, well, maybe that didn't work out. Why did it not work out? To actually, in some cases, completely open up a new question that people wouldn't have thought of, right? So that's also a consequence of building the Lego set wrong, right?
Never stop playing with Legos.
Never stop playing with Legos.
Yes. Oh my gosh, this has been a great conversation. And thank you so much for adding a lot of clarity to the work that you're doing. As we wrap up today, what would you like to leave listeners with, especially those people who are outside of science and nanotechnology? What do you want them to know about what's coming next from your lab?
What I want people to know is, whether they realize it or not, there is an incredible amount of necessary, I would say, new knowledge generation, creation of new knowledge that is required before any of the things that they interact with on a daily basis in their lives can actually come to fruition. And in some ways, the goal is not for everybody to know everything that goes into, let's say, their iPhone, but yet it's an incredibly enabling technology, right? There's examples of this all around us in all of our daily lives. What we are really aiming for, both in my lab at Northwestern and the IIN, everybody who's affiliated, right? We are really trying to lay the groundwork for the next generation, the future of what we as a society have available to us. If you really believe in what the future is, if you believe that we should have a better future as a society, then what you cannot compromise on is supporting efforts to actually do that, I would say. And I think that really boils down to, even if you don't know what's all under the hood of things that you use on a daily basis, you should not lose sight of the fact that there's been a lot of effort put into figuring that out in the first place. And it's an incredibly important cornerstone in society that should not be dismissed, ever, in my opinion.
Support your local scientists.
Yes. Yeah. It turns out we're usually cool people too. So, yeah.
James, thank you so much for coming on the show today. We appreciate all of your time.
Yeah, of course. Thank you for having me. It's been a pleasure. I really enjoyed it.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.